A piecewise function is a set of pieces of functions that you put together to make one single function. So, if you notice in number 1, we have 3 pieces. Our first one is linear, 2x plus 3. Our second piece is quadratic, x squared plus 1. And then our third is constant, so it's just 5. So, how do you know which function to work with? Well, it all depends on the restricted domain right here. So, we're first going to evaluate piecewise functions. So, where is x, -1, in the domains on the left? So, -1 falls into that category, which is less than 0. So, this means I'm going to do 2 times -1 plus 3, and that gives me 1. So then f of 0 falls into this category because we have the equal to 0 on this inequality symbol. So we have 0 squared plus 1, which equals 1. F of 1, x, is 1, which also falls into that middle category. So now we have 1 squared plus 1 equals 2. And then that last one, f of 6, is greater than 5, and there's no x to plug it in for because it's a constant function, so all the values for y are going to be 5. So now let's graph. So to graph these, I'm going to draw an xy chart for each of the 3 pieces. So since for number 1, 2x plus 3, x has to be less than 0. I'm going to start at 0. I need to always include that number 0, even if it says less than and not equal to. And then a couple points less than that. So if I plug in 0, I get 3. If I plug in -1, I get 1. If I plug in -2, I get -1. So I'm going to graph those. So at 0, 1, 2, 3. Now, that's going to be an open circle. So when I do my chart, I'm also going to identify that this is open. And since it says everything less than 0, that means we're going to actually have an arrow on the other side because it's going to continue less than 0 forever. So then I have -1, 1. And then I have -2, -1. So this is a line. And now I'm going to add on an arrow at the other end because it continues everything less than 0. All right, so for a middle quadratic piece, this xy chart. Now, this piece has 2 endpoints because it has 0 and it goes to 2. So we have to include everything in between 0 and 2. So I have 0, 1, and 2. Now, I know 0 is going to be closed because it says n equal 2. And then 2 is actually going to be an open circle because it doesn't equal 2. But we still have to go to 2. So if I plug those in, I get 1, 2, and then 5. So if I graph that, at 0, 1, it's a closed circle. And then at 1, 2, and then at 2, 5, it is also, no, it's open. Sorry about that. So it's an open circle. Now, this is a quadratic, so you have to make sure when you connect the points that it has that curve to it. It's a quadratic, but it's just a piece of this quadratic. All right, and then our last one. So everything that's at, it says x is greater than 5, so we're going to go 5. It's open because it doesn't say n equal 2. And then 6, 7, and then we're going to actually keep going down because it says everything greater than 7, so or 5, so it doesn't have an endpoint. So if I plug in 5, and then once again, you can't plug in 5, so all the y values are 5. There's no x there to plug it in for. So I'm going to go to 5, 5, and I have an open circle. I have 6, 5 as a point, and then I have 7, 5 as a point. And this is also a line with an arrow at the end because it continues on forever. Now, domain and range. Domain is the farmost left point to the farmost right point. Well, farmost left point is down here. It's an arrow. So that means I'm coming from negative infinity, and I go all the way over. Now, right here, there's a break in this graph because of the open circle, but if you notice that we also have a dot at x is 0. So we're good. We can keep going. So then we go all the way over to this point right here to 2. And we need to include a parenthesis because it's an open circle, and then in union with, and then we have this big space right here. So we're going to skip over that and start at 5, again with an open circle, so it's a parenthesis, all the way to infinity. And now my range the lowest point in my range is down here. It's also an arrow. And then it goes all the way up. Again, we have an open circle, but there's a point right here, so that number is covered. And then we have an open circle at 5 and another open circle at 5, but all of these points here take care of the y value being 5. And that is going to be our highest point. We include it because all of these over here have a y value of 5. And that's where we stop because that line continues right forever and doesn't go up any further. All right, so some vocabulary. We first have a relation, which is a correspondence between sets. A function is a relationship that maps each input to exactly one output. The vertical line test is a method for testing graphically to determine if a relation is a function. And again, you can only do this graphically, so you have to be given a graph to be able to use or test with the vertical line test. And continuous means it's smooth, it's connected. And that's referring to the graph. The graph is smooth or connected. So basically, like if you were to trace the graph that you drew, do you have to lift your pencil, yes or no? So if you don't have to lift your pencil and you can trace the entire function, then it is considered continuous. If you do have to lift it, like in the example we just did, you would have to lift it. That's not continuous, and we actually call it discontinuous. The biggest mistake I see on this is that you think that continuous means it goes on forever in a direction, meaning there's an arrow, which is simply not true. It can continue to the right, left, down, or up, but continuous refers to the whole entire graph itself and whether or not it is connected or not. Okay, so example 2 has a linear piece and a quadratic piece. So we're first going to just start by evaluating. So h of 0, that x value is going to fall into the first category. So we have negative 0, which we know is 0, plus 8, and we get out 8. And then h of 3 is also in that category. So we have negative 3 plus 8, and we get 5. And then h of 8 is in the second domain, so we're going to plug 8 in. Negative 1/4 times 8 minus 5 squared plus 9, which is negative 1/4. 8 minus 5 is 3 squared, which is also 9, plus 9. So you get negative 9 over 4, and then if I made a common denominator, it would be 36 over 4. And if you added those fractions, you're going to get 27 over 4 as your output value. You have a calculator, use it. Yes, decimals are accepted. So this table right here basically is a way of organizing what I did with the XY charts on the first example. So this is the kind of format that we're going to be working with. However, in the notes, I have given you very guided choices. You're not going to have all this stuff on a test or a quiz. You're just going to have that header, and then you have to fill out the rest. So this is guided, so make sure you look at other examples in your homework to know how to fill this out completely on your own. So first, we want to separate each of the piecewise functions into the two pieces. So I wrote the first piece up top, which is x minus 8, and it's a line. I would also accept linear, because that's the function. The domain, well, we're just recopying where the domain is in between 0 and 3. And then this corresponds to the input values we have. Now we have two endpoints because there's two numbers on either side. So you have to include 0 and you have to include 3. It's always nice to include the numbers in between, and since 0 and 3 are pretty close, it's easy to do. But let's say it was 0 to 10. Well, you don't have to include every number in between those two, but you have to include 0, you have to include the 10, and then maybe a couple in between. All right, so for this problem, the only other thing to add in, because I did the input and output values for you, is to note that this value at 0, 8 is going to be a closed circle, and so is 3, 5. And I know they're closed because it says n equals 2 in the inequality. Okay, and then we have that quadratic function. I actually would prefer seeing quadratic. That is what we've named it before. And all this means is that, yes, we know it's a parabola, and transformed means because we are going to the right 5, we're going up 9, we flipped it, and we're getting a little bit wider. So that's what that means. So a quadratic function here, and once again, we just recopy that domain we're given. And then the input values, I did go from 3 all the way to 9, but you don't have to if you know what a quadratic looks like. A couple would suffice as long as you curve it. 3 is going to be open because it's just says less than, and then actually we're going to add in that 9 down here is going to be closed. And yes, you can plug this in your calculator, and you can even look at your table and just copy down the values there. But we're going to get 3, 8, 4 and 8.75, 5 and 9, 6 and 8.75, 7 and 8, 8 and 6.75, and then 9 and 5. So make sure you copy this down, and now we're going to go and graph it. Okay, so I'm going to start at 0, 8, and I know that that's a closed circle. And then I have 1, 7. I have 2, 6. And I have 3, 5. Again, both endpoints there are closed, and I have a line connecting them. All right, well, that looks like a line, and I said that it needed to be a line. Okay, so my next one is my quadratic. I'm going to go 3 to 8, but it's going to be an open circle. So up here, it's an open circle. And now I have 4 and 8.75, 5 and 9, 6 and 8.75, 7 and 8, 8 and 6, and 6.75, and then what do I have? I have 9 and 5. And again, that 9 and 5 is going to be closed. So this is my quadratic. I see the curve. You have to know what it looks like to connect it appropriately, and that is our piecewise function. So now if we did the domain, the farmost left point is right here. So I'm going to start from 0, and I have a dot there. I include it, so I have a bracket, and it goes all the way over to 9. Now I know it is discontinuous right here, but if I were to draw a line at x equals 3, I do have a point. I do have a y value there. It's not the open circle for the red, it's the closed circle. So I included that number, and it continues on, so that's why we can go from 0 to 9. And again with a bracket because we have a point at that value too. So then for the range, this is my lowest point, which is 5, and we include it. And again, right here, it's discontinuous, but I have a value right here and over here that takes care of there being a y value at x is 3, once again. So we go 5 all the way to 9, because that's the top of my quadratic function with a bracket. Okay, so for number 3, g of negative 2, negative 2 goes into the second one. And because here it's included and here it is not, so we know it goes in the second one. G of 0 also goes in the second one, and then g of 5 goes into the third. So when I ask you to evaluate, I don't have to use every single function. However, we will graph every single function. So for the first one, again, a lot of it's filled out for you. It might not always be. So it's a line, or we can say it's linear. I recopied my domain. I know that negative 2, it's open, and then since it says everything less than that, that is why I included this arrow right here. Now, for my output values, I'm going to get negative 2, negative 3, negative 4. For the second one, we can call this quadratic. I have my domain restriction, and then because it says from negative 2 including, this is closed, and it says less than or equal to, I'm sorry, I didn't mean to say including, I actually meant to say an equal to. So since they both are equal to signs, both of these endpoints are closed, and I have to include those two values. When I plug those in, I get negative 5, 0, 3, 4, and 3. And then that last one is a line. You could also say linear, or you can even say constant if you'd like. Everything greater than 2. So at 2 it's open because it doesn't say n equal to right there. And since it doesn't have another endpoint, we have an arrow. And then we're going to have 3, 3, and then obviously everything else is going to be 3. So let's look at the graph. So I'm going to graph negative 2 with an open circle. And then I have negative 3, negative 3. And then I have negative 4, negative 4. And then it's an arrow. So I'm going to continue this and make sure that I draw an arrow on that side. In the middle, I have negative 2, negative 5 with a closed circle. I have negative 1, 0. I have 0, 3, 1, 4, and then I have 2, 3. All right, so this is my quadratic function. And then the last part, now at 2, 3, it's an open circle, but at 2, 3, we already have it being closed. So once one of the functions closes the circle, it is closed. You can't reopen it. So you can draw an open circle around it, but honestly, I would just leave it be and close it in because we know that it's completely closed. And then everything else on this line is up at 3. So this is our function with an arrow on the end. This is a discontinuous graph, but every point, this is where it's discontinuous, but I have a point down here for the x value at negative 2. So my domain is actually going to be all real numbers. And my range comes from negative infinity, but then it does have a highest point up here, up at 4. And then it goes to the right forever. It doesn't go back up. And then we have a point at 4, so we're going to use a bracket. And our last example. So our first piece is a line, and then our second one is an absolute value function. And j of 1 goes into the first one. J of 2 also goes into the first one because of this n equal to. And then j of 3 goes into the second one. So if I did if I did -1 plus 6, I get 5. If I did -2 plus 6, I'm going to get 4. And then for the last one, if I do negative the absolute value and I plug in my 3 minus 4, 3 minus 4 is -1, takes the absolute value of that, which is +1, but then you have that negative out in front here, so it still is -1 plus 3, which gives me 2. Now, I just remembered back here, I didn't write those in, so I want to give you those values. You're going to have -5, 3, and then you have 3 when you plug them into the corresponding graphs or functions, so I apologize for that. Okay. All right, so that's my evaluate box, and I'm going to come down here and I'm going to fill out anything that's missing. I have the piece, I have the name, I have my domain restriction. I know that 0 is open, and then at 2 it's going to be closed, so I'm going to add that in. And then the output values go 6, 5, 4. Everything looks good for the absolute value. They're both labeled open, and we do 1, 2, 3. Okay, so if we were to graph the first piece, we're going to have 0, 6, and it's going to be an open circle. Then we have 1, 5, and then we have 2, 4, closed, and this is my line. And then I have 2, 1, which is an open circle. I have 3, 2, and then I have 4, 3, which is also an open circle. And this is my graph. The biggest mistake is that even though it's an open circle, we forget to include it. Anytime you have it in the domain restriction, you have to find where then you're going to have an open circle. You can't just ignore it, say it's open, which means it's not really there, so I'm going to skip it. And if you did that, then you would be missing all your values because you have to include everything between those two numbers. So my domain is going to be 0 to 4, and since 0 is open, I have a parenthesis, and since 4 is open, I also have a parenthesis. And then my range, parenthesis 1, for right here, and it goes up to 3 with another parenthesis, and then it skips up to 4, so I have to include this separation right here in between the graph. This is a space, so I have to jump all the way to 4. It's closed at 4, and then it goes up to 6, and it's open at 6.